Welcome to this unit on Chapter 12, MRP and ERP. MRP stands for Material Requirements Planning. We'll cover that first. And then ERP stands for Enterprise Resource Planning, and that will be our last topic that we'll cover in this chapter. Now, there's going to be a couple of other units, a couple of other lessons on this particular chapter besides the lecture slides here, so make sure that you take a look at all the material because there's a lot to learn here in this chapter. Now, I'd like to begin the lecture. Well, here's the learning objectives, so you may want to pause the lecture, take a look at the learning objectives, and then would you finish that, then begin the lecture again. From a historical perspective, MRP traces its roots back to the mid-1960s. Dr. Joseph Orlicki, who was a researcher at IBM at the time, is credited with the development of MRP and is generally known as the father of MRP. Dr. Orlicki wrote a very famous book titled Material Requirements Planning. That's still available today. On a personal note, at one point in my career, working as a systems manager at Texas Instruments, I was responsible for implementing a major MRP software project there that took about 3 years in total to complete. And Dr. Orlicki's book was a constant companion to me. I must have read that book about 25 different times. But again, getting back historically, shortly after he had published his initial paper on MRP, IBM, the company he was working for, as well as other software companies, began to write the software code that would essentially perform the MRP algorithm that Orlicki had espoused. This became so successful that the decade of the 1970s is generally referred to as the Great MRP Crusade. And it's called that because literally thousands of companies in the United States as well as around the world implemented the MRP software from IBM as well as other software companies to take advantage of this new algorithm and this new capability. Now, there were a couple of things that really enabled Orlicki to have kind of a breakthrough in the way that material planning was performed up until this time. And one of the breakthroughs was that he realized that there were essentially two types of demand. One type of demand is shown on this slide. He called it dependent demand. And the other type is shown on this slide right here, which is independent demand. Now, independent demand is defined to be the demand that is literally independent of anything. Independent demand is almost always going to be for the finished product that we are selling. So let's take a product that we all recognize as an example, and that would be an iPhone. So the independent demand for the iPhone would be that demand for the finished iPhone telephone that's ready for a customer to purchase. The dependent demand would be the demand for all of the materials that go into the iPhone. So that would be the display, as well as the microprocessor, the memory chip, all the other circuitry that is part of the iPhone. All that is dependent demand. And of course, the demand for it depends. It's called dependent demand because it depends on something. What does it depend on? It depends upon the demand for the independent demand. Now, the reason why these two types of demands are important is shown in this slide here. Independent demand tends to be fairly stable. Your textbook refers to it as fairly stable. In other words, over time, it might not change dramatically. There will be some change in independent demand, but it doesn't change dramatically. On the other hand, dependent demand, again, as a refresher, dependent demand would be that demand for all the materials that go into the iPhone, the display, all the chips and memory and everything tends to be lumpy demand. Now, what do we mean by lumpy demand? It means that you need a certain quantity on a certain date. So you'll see in the upper right-hand corner of the slide, you'll see a blue vertical bar. So I need a certain quantity. Then I go a period of time where I don't need any. Then I need a few a little bit later, and then a few a little bit later. It is certainly anything but uniform. And it is the issues that occur with dependent demand is what makes life so interesting and sometimes so difficult for manufacturers that are building a product. So let's try to relate these two concepts, independent demand and dependent demand, to something else that we've already covered in the course, and that is a supply chain. So you should be familiar with supply chains at this point. Supply chains is that linkage of organizations that are producing and delivering a product all the way into the final customer. So if we take a look at the supply chain diagram in this slide here, this is a retail supply chain. Again, we'll use the example of an iPhone to discuss these concepts. So we have a final customer that could be you or I, and we're going to go to some retailer. It could be Sprint, it could be AT&T, it could be some other company that we could buy our iPhone in order to buy it. So the demand that we would have for that retailer is independent demand. That is the demand for the finished product. That's what we want. But all the other companies in the supply chain, the producer of the iPhone, which of course is manufactured in China by a company in China, as well as all the companies that produce the memory chips, as well as the other circuitry, the display, and so forth, all of their demands are going to be dependent demands. So that's the part of the supply chain that is going to have a need for material requirements planning. So the bottom line is this. Anytime you have the issue of planning dependent demand, you're going to need MRP. You just can't get the job done without MRP. So what is MRP? Here's a definition of MRP. It is a computer-based information system. Now we're going to do MRP in a homework, and we're going to have another lecture in which we're going to do MRP using a spreadsheet. But in the real world, you just can't do MRP using spreadsheets. It's just too complicated. It takes too much time. You're going to make too many mistakes with a spreadsheet. You have to have a computer information system to do MRP. And what does this information system do? Well, it's going to have certain inputs, and we're going to talk about those more in greater detail in this chapter, but it's going to take as a minimum some type of master schedule requirements. We have to know what our demands are for our end items. Another word for end item is our finished product. So finished product and end items are the same thing. And then it's going to take that information along with the other information and determine what the requirements are for all the other things that go into the product. So again, the display, the memory chip, the microprocessor, and so forth. So MRP is basically going to be answering three primary questions, and that is what materials are needed, how much material is needed, so we need to have a certain quantity of this particular material, and then there is a time-related question that's also going to be answered, and that is when is this material needed? So I need a certain quantity of this particular material, and I need it on a certain date. Now, there's another question that MRP could possibly answer that we could potentially add to this list as well, and that is if this material could be acquired from more than one company. MRP could also answer the question, who are we going to acquire it from? So we refer to that decision as a sourcing decision. So this slide shows from a graphical point of view all of the inputs that's going to be going into this computer information system program and the outputs that come out of them. So we can see that there's three inputs that come into the software program. One is the master schedule, which we have already covered in another chapter. Another is the bill of materials, which we'll talk about in this chapter. And then the third piece of information is inventory records. So all of these inputs, the master schedule, the bill of material, and the inventory records, we're assuming that all of this information is also computerized and on the same server that the MRP program is on. So basically, we're just going to be taking this information from the database that exists, and the MRP program is going to be processing it. And then there are some outputs that come out of MRP, and we'll talk more about those outputs in later slides in this chapter. So let's go into the inputs, and beginning with the master schedule. So the master schedule is going to essentially define what our demands are, and typically the master schedule is going to show the demands for the finished product, or we could also refer to that as the end item product. And of course, the master schedule is going to not only have the quantity that is needed, but it's also going to have the time in which these are needed. So the master schedule could consist of forecast demands, and the master schedule could also have built within it actual customer orders where customers have already placed orders for our particular product. Now, it's important when we do master scheduling that the length of time into the future in which we do the master scheduling needs to be at least equal to what we refer to as the cumulative product lead time. So this cumulative product lead time, the definition in your textbook, I know it's a little bit confusing, so let me give you, which I hope will be a little bit simpler definition of what cumulative product lead time is. Cumulative product lead time is this. If I was producing a product, so let's say that I'm producing iPhones, if I had no inventory of any of the materials that go into an iPhone, I had no displays, I had no memory chips, I had no microprocessors, I had no inventories of any of those. How long would it take me to produce the first iPhone? So it is the accumulation of all the times it takes to acquire all those materials and then to do whatever assembly and testing and whatever else is required for me to say I now have a product that can be shipped to a customer. In another lecture, I'm going to have you go through some calculations where you will actually calculate what the cumulative product lead time is. So be sure to go and view those other lectures that will be part of this. So here's another look at the cumulative product lead time graphically. So again, if I had no inventories whatsoever of anything, we see we have a block on this slide called procurement. So that would be how long would it take me to procure those materials from some supplier. And then after I had procured them, there could be some fabrication possibly that I have to do. So fabrication is defined to be some type of process where I'm taking those raw materials, converting them into something else. Then there could be some sub-assembly work that I have to do to take to some of those fabricated parts and then to assemble them into another stage and then take those various sub-assemblies and link them all together into the final product. So how long would it take me to actually get that first part out? Another input into MRP is the bill of materials. We may also refer to the bill of material as a BOM, a B-O-N. Sometimes joke around in class that, if you're getting ready to catch a flight, you're going through security at the airport, and you're talking about bill of materials with your colleague that's traveling with you. That's not the time to use the acronym BOM when you're talking about bill of materials, because the security people, if they hear the word BOM, they're going to think it's the other type of BOM, not a bill of material. Bill of materials are also sometimes referred to as a product structure tree. So what is a bill of material? It's a listing of all the assemblies, all the materials that go into a product. So for the iPhone, what are all those materials that are needed to make that product? Another way of describing a bill of material is it's very similar. If you were going to bake a cake or you were going to do something that required a recipe, the recipe for that cake or whatever it is that you were cooking is going to list all the ingredients that goes into that particular cake, and essentially that's the bill of material. Bill of materials is sometimes referred to as a product structure tree. When I was working for Texas Instruments, we sometimes referred to bill of materials as a Christmas tree. We call them a Christmas tree because a Christmas tree comes to a point. So a bill of material is typically graphically oriented. So at the top of the Christmas tree that represents the finished product, and then the Christmas tree branches out. It gets bigger as you go down, and a bill of material quite often does the same thing. It gets bigger as you go down to the various sub-assemblies. Not always, but many times it does. So here's a graphical view of a bill of material. The finished product in this case is a chair. So the chair consists of a seat. It consists of kind of a back, which has some back supports and some crossbars and some side rails. It also consists of the front legs, which has two front legs, and it also has another crossbar that goes across those front legs. And then below that is the graphical view of the product structure tree, or the Christmas tree. So at the top of the Christmas tree is the finished product, the chair, and then the next level down are the two sub-assemblies. The two sub-assemblies are the leg assembly and the back assembly. And then we have the seat, which is not a sub-assembly because there's nothing in that goes below the seat. And then the leg assembly and the back assembly shown the materials that are needed for those two particular sub-assemblies. Bill of materials have what is referred to as a low-level code. Now, I've always thought that whoever came up with this term low-level code really was not using correct English grammar. I think from a correct English grammar point of view, what they should have called it is lowest level coding. Lowest level coding as opposed to low level coding. And the diagram that's shown in this slide, we see that our finished product, in this case, is product X. So the finished product is, by definition, referred to as level 0. And in order to make X, it requires 2 B and 1 C part. And that level is referred to as level 1. And to make the B's requires 3 D's. And to make the C requires 2 E's. And that is level 2. So each level that we go down in the bill of material or the product structure tree, the low level code increases. Now, let's take a look at the diagram, and let's look especially for part E. And if you look at part E, you'll see that part E occurs 3 different places. Okay, we have part E that is needed to make part C, and we also have part E that's needed to make part D and B as well. So we see that part E, as in Edward, exists on level 2, and it also exists on level 3. So on this bill of material, the lowest level where part E exists is on level 3, the lowest level. Now let's take a look at another example, a different material. Okay, so in this case, our finished product is product Z. And again, let's take a look for the part E. So in this example, we see that part E appears just on one level, level 2. But on the previous slide, part E is low-level code on the previous part. Part X was level 3. So the question is, on all the bill of materials, let me say that again, on all the bill of materials where E exists, and there could literally be hundreds of bill of materials where part E is used, what is the lowest level that it exists on all of those bill of materials? So in these 2 slides, the answer to that question is level 3. The low-level code for part E is level 3 because that is the lowest level that it appears on these 2 bill of materials. Now, the other thing you might notice on this slide is the numbering of the low-level codes, beginning with level 0. And there's only one type of profession who likes to number things beginning with the number 0, and that is programmers. Computer programmers love to number things beginning with the number 0. So this kind of implies to us that this low-level code thing is a computer software thing, and it is. It is a computer software thing. And it's important for the MRP computer program to know what the low-level code is for an item. And we'll talk about the reason for that in a few slides coming up. One more input for MRP, and that is the inventory information. Okay, so the inventory information, we need some information not only on how much inventory we have of a particular item right now, but we also need to know if we have some orders that we have placed for that particular inventory item, and we've placed those in the past, but they have not yet come in yet. We also need some information on how long it takes to acquire that item. That's referred to in this slide as the lead time. We also need to have some policy information called the lot size policy, which is also part of this inventory information. So again, all this information, the inventory records, the bill of material, the master schedule, we're assuming that all that information has been computerized and it's on the same computer server that the MRP program is going to be running from. So what MRP is going to be doing, it's going to be creating schedules for things. So this slide shows the concept of an assembly chart. So if you take a look at the horizontal axis at the bottom of this slide, you'll notice that a little past week 11, we have that this is when a particular item is needed for delivery. And if we know how long it takes to perform each of these tasks, each of these assemblies, that is the lead time, MRP can perform what we refer to as backward scheduling. Working backward in time from some future date is what backward scheduling is all about. So the MRP processing is going to take the inputs that we referred to earlier, the master schedule, the bill of material, the inventory information, and it's going to process all of that. Sometimes the term explode is used. Now, we're not referring to the literal explosion definition here. What explode basically means is that it's going to take that and it's going to go through each of them in a very organized fashion and determine what the time-phased requirements are for all the materials. So when we say time-phased, what we're talking about are two things: that we need a certain quantity of a certain item, and we need it on a certain date. Needed on a certain date. So we refer to that as time phasing the demands or the requirements. So MRP, typically the way we do MRP, the way we teach it is we use kind of a spreadsheet, but again, in the real world, you can't really do this by spreadsheets. But this slide shows some of the important terms that are used in the MRP processing algorithm. You'll see in this slide that the top row has the two words gross requirements. So anytime that you see the word requirement, it's referring to as a demand. A demand is something that you need. And the word gross indicates very similar. If I'm sure everyone has worked at some time in their life and they've received a paycheck, and on your paycheck you have a gross pay and you have a net pay. So the gross pay is your pay, which is basically the hours that you've worked times your hourly rate, something like that. The next term in this slide is referred to as a scheduled receipt. Now, a scheduled receipt is not a demand. Let me say again, it's not a demand. It is, in fact, what we would refer to as a supply. It is an order that you have previously placed for this particular inventory item, but it has not yet been received. It is going to be received. It is scheduled to arrive at a certain date. Projected available. Projected available is the projected inventory that we will have on hand at some future date. So I said at the beginning of this lecture that Dr. Orlicki had two breakthroughs that allowed him to create this MRP processing algorithm. And the first one was the recognition of the two different types of demands, independent and dependent demand. The other breakthrough was this concept of projected available, that we could, in fact, calculate what the inventory will be at any future date. And so, as long as that projected inventory is either a positive value or 0, we are okay. So I like to suggest to students that projected available is very similar to the checking balance in your checking account. So as long as the balance in your checking account is either a positive number or 0, you're okay. It's only when that is a negative number that you're not okay. So what MRP is going to be doing is going to be calculating this projected available inventory until it becomes a negative number at some point in the future. And when it becomes a negative number, that indicates that's when we're going to run out of inventory. And we're going to need to do something about that. So we're going to need to make sure that inventory arrives on that date so that we do not, in fact, run out of inventory. A couple of other rows on here, net requirements, okay? Again, going back to the paycheck example, net pay, net requirements, that is the actual amount that's needed for each time. Planned order receipts. So whenever the projected on-hand balance becomes a negative number, that indicates that we need to have a certain amount of inventory arrive on that particular date. And what MRP is going to do is going to be creating something called a planned order. So a planned order is a order to create more of this particular inventory item, either through production or through purchasing. And there's a certain quantity that we need, and we need that quantity on a particular date. So the receipt means this is the date in which we need it. The planned order release is the planned order receipt date minus whatever the lead time is for this item. So let's take, for example, if I had a projected on-hand inventory of a certain item of -10 in time period 6, my net requirement is going to be 10. My planned order receipt will be 10 in time period 6. That's when I need them to come in, so that's going to cover my projected shortfall in that same time period. Let's say it takes one time period to acquire them, so the planned order release would be 10 in time period 5. So MRP development, okay, it's going to time phase all these requirements, and it does what is referred to as level by level planning. In other words, it starts with low-level code 0. It always starts with low-level code 0. It's going to plan all the requirements for the finished product, and then it's going to take the result of that plan, and it's going to carry that result down to the next level, level 1. It's going to plan all the material at level 1. And when it's finished planning all the material at level 1, it's going to take the results of that level and carry them down to level 2 and continue that process until all the levels have been done. That's going back to low-level code and the importance of low-level code. So if I have an item that exists on level 2 in one bill of material and on level 3 in another bill of material, its low-level code will be level 3 because that's the lowest level it up. So when MRP does level-by-level planning, when it gets to level 2, it cannot complete the planning of that item at level 2 because there are going to be some additional demands for a different item when we get down to level 3. So we can't complete the planning of that item until we know what the total demand is. So that's why low-level code is important. So if I know the low-level code is 3, then I can only complete the planning of that item when MRP reaches that level 3. So there's an example here of the MRP algorithm, but what I'm going to do in the lecture here is I'm going to create a separate lecture in which I'm going to go through all the MRP algorithm. So we're going to conclude the lecture at this point, and then I'm going to ask you to go view that other lecture in which I'm going to be using a spreadsheet and going through the process. So this is going to conclude part A of this chapter.